Oh, hello. Good afternoon, Mark. Good afternoon, Weishi.
Hello, Professor Yarbaum. We're all in one.
Oh my gosh. Oh, okay, great. Wow. Hello, hello. So that's amazing. I've never seen that before. That's tons of class. That's 3 times as much class participation points. That's amazing. Wait, so it's Gabriella and who, just so who else is? We can't see. Oh, wait, more. Well, hello. Okay. And, okay, great. Good afternoon, Alyssa. Good afternoon, Andrew. Good afternoon, Charlie. Good afternoon, Jayla. Good afternoon, Catherine. Good afternoon, Catherine. Good afternoon, Stephanie. Good afternoon, Jaylyn. Good afternoon, Vivian. Okay, now let's see who. Oh, and so can you wait, who is with Gabrielle? Can you, because I can't even see through the masks and the haze and everything. Can you tell me who that is with Gabriella and
Celine and then Rachel. Yeah.
oh, great. Okay. Oh, hello. All right. Great. Awesome. Thank you. Oh, more people. That's fantastic. Good luck to us all making this work. Okay. And who else have I not said? So, and hello, Weishi. Hello, Andrew. Hello, Gabrielle. Hello, Jaylyn. Hello, Jayla. Hello, Charlie. Hello, Alyssa. Hello, Stephanie, Mark, Catherine, Vivian, Lakshmi, and now Sophia's coming. Awesome. Hello, Sophia. Awesome. Okay. Hello. All right. So we are here. That's good. And we are going to get rolling. We're going to do some logistics for, oh, more people. Sorry. Okay. And I totally appreciate, again, and those of you who don't know me, I totally appreciate those of you who are showing video. And if you don't know me, if you didn't have me before, you do get extra points for that. We'll talk about that too. We're going to talk about all this, but there, with the whole game turns aside, let me back up for a second. I got game turn 1 and 2 from many of you. I totally appreciate it. If you haven't gotten it back yet, that's on me. That's not because you did anything wrong. In fact, I may read the names out in a moment. It's the beginning of the semester and already I'm completely behind with all this physics chaos. So I will probably read the names out. Not that did anything wrong, but that did things right. I got the game turns from you. If you haven't gotten them back yet, that is not because of anything you did wrong. That is on me. And those of you who don't know me, those game turns, those are daily, just daily 5 points. How much did I, do? Can I remember a moment where I participated today? But those of you who do know that, oh, I think I just lost. Oh, I just lost the screen. I don't know why that happened. Pardon me for a second. I don't know why that just happened. Wait, I am still there. Why did that? Hang on. Okay, I think we're back. I think my internet connection is as wobbly as my psyche. Why? So, okay, something is very slow here, but besides me, with the game turns, again, some of you know this already, some of you don't, but like as we get rolling into the semester, other types of participation portals will be opened, all voluntary, all voluntary, but there will be portals that are open where if you ever, for example, show video, as some of you are doing today, which I totally appreciate, Jayla and Jaylyn and Andrew and Gabriella and Weishi, I totally appreciate the fact that you're showing video. There'll be a portal soon opened where you just write in, yes, I showed video on Monday the 7th, whatever today is. And you don't have to prove it or anything. You just say, yeah, I showed video on that, and you'll get points for that. If you show video on another day, you'll tell me that and you'll get points for that too. And again, no one has to show video, but anytime you do, you will get participation points for that. Same thing with those of you, and some people, again, some people know this from last semester, some people don't, but like, for example, like Mark right now, or Catherine with a Y, they're not showing video right now, but they are showing something in their square that helps me a little bit identify them, like they're showing an avatar or whatever. A portal will be open for that, where you could just ever say, again, they don't have to do that, and you don't have to do it every time in order to get points. But if you ever feel like doing it, then you'll be able to just write in the portal, yeah, I showed an avatar, just had a letter J in it or whatever, February 7th. So please give me points, and you'll submit that in, and I'll be like, oh yeah, they did. And then you'll get points for that. Not so, and other things too, like if you ever use your voice, but we have to start opening these portals soon. We just still have to get rolling. So again, if you're not showing video, it's not a problem and it's no shame, no blame. But if you are, just like, thank you. And that's cool. And that's helpful. And you get points. All kinds of participation recorded in that fashion. Okay. So that's number one. And so again, also a long way of saying, if you did already turn in 2 game turns, that is you are supposed to do that. And thank you. And I'm sorry, I haven't gotten back to you yet. I will catch up shortly. Number 2, we're going to get to mostly today. We're going to start. We are not going to finish, but we are going to start going over somewhat methodically and mathematically the thing on a spring homework that was technically due today. I asked you to make a best attempt. I totally understand it may be raw or unfinished or unsure, but I asked you to make an attempt. Many of you did, about 8 of you did. I totally appreciate that. I wasn't even pretending or planning to get them back to, therefore today. Let me in fact just quickly say, hold on. Hang on 1 second. Yeah, so this is just, so about 6 people have not turned it in yet. That is fine. Again, no shame, no blame, and I'm certainly not going to say your names or anything like that. I want to make it clear again that we're going to get rolling on this sheet today. That might help you get started. That might help you know what it is I'm looking for. So please, 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 there's no problem with turning it in after today. None at all. And it's not cheating. Please pay attention today, and hopefully today will help a little bit. But at the same time, like for sure, I just wanted to thank you, Stephanie. Thank you, Celine. Thank you. Oh, and also let me just say again, if I'm still mispronouncing some of your names, please let me know. It'll take me a little while. I think that's right, but please forgive me and please correct me until I get it right. But so this is a quick just shout out, like, thank you, Stephanie. Thank you, Celine. Thank you, Jalen. Thank you, Josephine. Thank you, Alyssa. Thank you, Michaela. Thank you, Jayla. Thank you, Nicholas. Thank you, Shagupta. Thank you, Mark. Thank you, Brenda. Thank you, Lakshmi. Thank you, Wishi. Thank you, Vivian. Thank you, Catherine, you can decide which with an I. Thank you, Andrew. Thank you, Gabriella. Thank you, Charlie. Just saying, I totally acknowledge that you totally made an attempt to get it in for today. I appreciate it. It's noted. I see it. But again, those people whose name, and if I didn't call your name again, let me say no shame, no blame. I'm just trying to, walk a fine line here, as always, karmically. If you did turn it in though, and I'm going to start talking about it soon. If you turned it in, and as I'm talking, you're like, oh, that's what he was looking for, or oh, that's how you do it, then you can resubmit. Please do. If you have corrections or improvements, again, I would recommend don't remove your old work, just submit new work. And you can write a note that says, please, grade the more recent one or whatever, or you can title the document like, look at this first or whatever. And I might well ignore the other one, but I'll just see that you're doing that much work. If you post a review, I know I've said this before, but never erase or blot out your old work. It's totally dumb. You should give yourself credit for doing work. I should give you credit. You should know that I know that you did it. But so all of you, if this class helps you in any way start to do or improve that assignment, then please take advantage of that. Last thing also, if any of you is new to this, or you're thinking, well, wait, he's talking a lot, but like, wait, was I supposed to do the homework for today or not? Like, what's the deal? Like, and if I didn't do it, he's saying that's it's totally, I could just always get away with that. What I'm saying is this. I'm saying no shame, no blame. I'm saying definitely better late than never, definitely, and definitely revised and redone better than not. But if the thing was due today, it is better to have tried it before we start today, because you'll get a lot more out of class and you'll contribute more to class. To do it before class is better, because then class will make a lot more sense and be much more efficient and productive for you. But yes, I will still always take things later rather than not at all. And yes, I'd like you to, the ideal thing is you try something, then we talk about it in class, then you try better and harder the next time. That's the ideal. Okay, I think that's clear. I think everybody's here. Okay, so we're going to start going over this thing on a spring thing in like one more second. There's one more logistical item though please remind me and stop me again if I'm like all over well, I am all over the place, but there's new people here. There's people I've had and there's people I haven't. So I'm trying to talk to both of you at all times. Please don't be shy about the direct chat stopping me or the public chat stopping me. One question though, in this section of Physics 204, this section, which is always going to be online with me here at this Zoom link, remind me actually, I'm going to remind you, I want to confirm something logistically here. For this section, your lab, right, okay. I just want to have a check-in on this. Your lab last Friday was remote and was covered by Professor J. Walters, i.e. a man, like the person that some of you had for class. Is that correct? That last Friday you had a lab? No. Yeah. Is that correct that you had lab? Oh, Tuesday. Wait, what am I saying? Wait, okay. I'm sorry. What am I saying? Hold on. Oh, I'm sorry. No, I'm totally wrong. Right. You're totally right. I'm sorry. I'm looking at the chat. Sorry. You had lab last Tuesday online with Woo. You had it Tuesday at 3:05 with Woo. That's what you're saying. Let me check the chat. That's correct. That's what you're saying. And that's correct. Tuesday. Right. You Woo on Tuesday. Right. Okay. I'm looking at the chat. Yes. Okay. Thank you. Okay. And I imagine that maybe one or two of you, I understand. I mean, there was confusion. So if one or two of you missed it or didn't get the Zoom link in time or whatever, you're not in trouble. Again, no, I never said this expression, no shame, no blame before, but it seems apt. Like no shame, no blame if you missed it, if you didn't get the Zoom link, because things are confusing right now. But either if you let him know that you missed it or let me know, like after, in a text message or something, and we'll work it out. But most of you made it, okay, and you had it. So let me confirm, right, so you had it last Tuesday. So tomorrow, of course, you won't have it, right, because tomorrow's Friday at John Jay, right? So there's no lab at all this week. Oh, good afternoon, Jalen, good to see you, sorry. And sorry, I'm all in the wrong place in the chat, sorry. Can I confirm, are we all on the same page that you just literally just don't have lab this week? Is that, yes, okay. So last thing, next week, in principle, like in theory, your lab should return to being in person as of next week. It should be in the lab room. And in theory, it should be with Professor Wu. However, there is a little bit of an issue right now because Professor Wu is stuck in China. I mean, that's why, like, he is supposed to be your instructor. That is the deal, but he is stuck in China and having a hard time getting out. So that's why it's online right now. And even though I know for some of you, you'd rather it just change to online for the whole semester, and some of you would not, believe me, but it's not a vote. And I don't even get a vote in that. The college policy is that we're not supposed to keep it online. And I know I probably said this live, I'm just trying to be clear. We're supposed to keep it in person because that's what we promised you. And that's what you're owed. So let's stay in tune with each other of exactly what's going to happen as of next week. Like it should go back in person and it should be him, but we're having problems getting him back into this country. So I guess if nothing else, I'm asking you Wednesday to remind me if I have any progress on the situation or any update. And I'm also encouraging you, if you don't get a communication by like this Friday as to of any change or update, you're welcome. All of you, any of you is welcome to email me or text me like this Friday or this weekend, like what's happening with our lab next Tuesday. I mean, it's something that I'm trying to solve right now, but there's so many moving parts in all of this that I get confused. So by next week, something is supposed to happen with your lab, and you are welcome to reach out to me and either ask me or remind me to, okay? Is that, okay, I'm just making sure. I sort of have to give that speech to every physics class right now because it's all right. Could someone just tell me if we're on the same page, or maybe that's what, maybe you already did. Okay, thank you, Alyssa. Okay, thank you. Okay, thank you. All right. So that's that issue. Okay. So now we're going to go to the sheet, a thing on a spring. and we're going to start going over it. And I'm going to I'm going to be a little slow at first. I apologize. The main equation that I sort of would think that you would use mostly to do the first few questions in the sheet is this F equals negative KX equation on the sheet here. Some of you may have literally seen that recently. Some of you may have not. Some of you might have found it on the web. Some of you may not. I'm going to talk about it, but that I would think that that's the main way to do the first, that and F net equals MA, Newton's second law, would be the main way to do the first few. But I'm also I'm going to walk you through the first few, also showing you my 5-step method of solving problems, which some of you saw last semester with me, but some of you did not. So that's part of my instruction today, is to show you this 5-step method for solving problems. And I would like you all to use it in homework and on exams from here on in, both when you think you know what you're doing and definitely when you don't think you know what you're doing. Okay, so we're going to turn to the sheet. Okay. Okay. Now, again, I want to be super clear about this. Again, I am aware this is maybe a little bit of a me thing. It's becoming more of a physics thing. But so Professor Jay Walters did not exactly do this last semester. I know that. So and that's fine. But so it's new to some of you. But those of you who did, that it's old to, we're doing it again. And I want to emphasize it again. This is what we're looking for you guys to do when you solve problems in homework and in exams. And also please know, especially if you're new to the class, that in a way, this is a rubric that I use for grading, particularly on homeworks. Okay, homeworks, you can get all the points on homework, even if all your answers are wrong, as long as you show these steps of problem solving work. Conversely, you could get all the answers right, but if you don't show these particular steps, points can be taken off. Okay, so this is the method of solving problems. The best thing to do with this method is to practice it with problems that you already think you do know the answer to. So like practice converting your quick mental answers into this sequence of steps. And that way you have a sequence of steps to do when in fact you don't know how to solve the problem. Okay, so again, I apologize if this is redundant to anybody, or maybe it's review, but I'm going to walk us through this in the context of this homework number 1 thing on a spring. So step 1 for solving any problem, every problem in physics. And again, you're doing your problems on separate sheets of paper. Like you don't try to work things out on our sheets. There's no room. You'll cram all your thoughts. We won't be able to read, blah, 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 blah. So on separate sheets of paper, you start solving whatever problems we're giving you. And the first step for any problem is what is DFP, which stands for, to me, stands for so here in this case, right? So the very first thing we do is present the actual facts of the problem. Like in now, and that's generally the very first thing that appears on any of our sheets, right? But we are going to transcribe it into our homework. So I mean, I'm looking at this sheet right now as I do this. Hopefully you have the sheet in front of you. I can't share the screen because I'm sharing this other screen, but I'm looking at the sheet now and I have a diagram. I'm going to give my own version of that diagram right now. And it's going to be my version. If I'm the student, if I'm you, you're going to give your version of the diagram. Don't assume that just because we have it in the questions that takes care of it. So here's my version. Oh, whoops, sorry. Okay, so here is everything. Okay, so here it's not the exact same picture, right? I mean, it's not a copy paste, but here's my version. If I'm the student, I'm doing this. Is the first thing I do is here's a diagram and all of the relevant facts of the problem. And the relevant facts are that we've got this spring fixed to a wall. It's a horizontal spring. It's fixed. It's rigid on one end. It's free to stretch or compress on the other end. On the other end of the free end, there's a mass tied to it. The mass, which we're calling M, has a particular value of 0.3 kilograms. The mass at the beginning of this problem, at t equals 0, at the beginning of this experiment, the initial position of the mass appears to be 15 centimeters. 15 centimeters, 15 positive centimeters, I should say. 15 centimeters, i.e. 15 centimeters to the right of what we're calling x equals 0. What is x equals 0? That's the equilibrium position of the spring. That's the place where the spring would, where that edge of the spring would just sit with or without a mass on the end if we weren't deliberately pulling it out or holding it somewhere else. Like that's the relaxed position of the spring. So right now we're deliberately holding the mass 15 centimeters to the right of that equilibrium position. And last, note what we're holding it there. So if once this experiment begins, once the stopwatch starts going and we let go of that mass, we're believing that we're calling that place 15 centimeters, we're calling it an initial position because it is the place from which the mass will be released, the place from which the mass would have an initial velocity of 0, and then begin undergoing the experiment. Lastly, the last fact of the experiment is that this spring is identified by a spring stiffness or a stiffness constant, or otherwise known as K. The K of this spring, the strength of the spring, is given as 200 newtons per meter. Apparently, that's how we identify spring. I mean, it is, but we could even just infer from these facts that the strength of the spring is measured and identified by how many newtons of force it exerts per every 1 meter of stretch to which we subject it. Okay. Now that's already, so all of that is the very first thing that I would expect, again, for all of you who, you know, whether this review or not, if you're going to turn in a homework or do an exam problem, the very first thing I would expect is that you present to me the facts that, you know, we presented to you, and you're going to present them on this fresh sheet of paper, such that I have enough facts now looking at this that I don't have to look at any other piece of paper to start analyzing this physics. Or I could give this physics to someone else who doesn't even know the assignment, and they could start analyzing or grading the physics as well. Or it could be a journal that you're submitting this as an article, blah, 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 blah. So that's the first step, is diagram and fact pattern. And there it is. Last thing to notice, and this is very important. Notice this step 1 diagram. Two things to notice. This does not look exactly like what's on the sheet, but it contains all of the relevant information from the sheet. In fact, arguably, it gets rid of some of the extraneous information. That's the goal here. One of the reasons you've got to write this down, I don't know why I'm yelling, sorry, I don't mean to be upset, but just one of the reasons that we want you to write this down, even though we just gave it to you, is the act of writing this down and copying it in sort of your style or your personality kind of forces your brain to extract the relevant information, and then also communicates to us that you know what the relevant situation, the relevant information of the problem is. It's like a very important step. So you do this, and here's my last thing. So it won't look like ours. It won't, and it's not a copy paste. Don't copy paste. You're actually going through the act of doing this. But also notice, last thing, this is a step. This is the first of 5 steps, right, of how to solve problems. Please notice, if you do this step, you get the points for doing this step. If you don't do this step, you lose points. And why am I putting you through this, or why do we care? Because notice that this entire step I just did, I don't even have any idea how to solve this question yet. In fact, I don't even know what the question is yet, but I know what the setup is. And by writing down the setup, some of the setup may in fact help me by the moment I get to looking at the question. But all of this that I just got points for writing down, I don't have to understand a thing yet about how to answer the question. It just is what the question is. So I'm getting points for that, because that's how we do physics. Like, we do physics 1 step at a time. All right, that's step 1. Now step 2. And please stop me, but this is step 2. Am I doing this? Oh, sorry. Okay, so now this is question 1, right? And I'm summarizing what the question is. The question is, at t equals 0, what's f? Or if you want to put it a different way, where x is 0.15, what's f? Okay, that's the question. You tell me that. If you're the student, you put that down. Again, notice like if we do this right, you'll be able to answer this, and I'll never have to look at a separate sheet in order to grade this, or I never have to be anything but good at physics in order to follow this. It's physics that's going to stand on its own when you do this. So this is what the question is: at t equals 0, what's f? So you just write that down, and again, you write it in like sort of your own terms or in notated, abbreviated terms, because you're just capturing the relevant information. So that's step 2. Now and you get points for that. And it's really important. You really got to show that you know what the question is before you start answering it, especially the harder the question gets, the more important it is. Now we go to step 3. Actually, let me go to the next. Okay. I might have lost. Okay. And tell me again if I lose. Okay. So now step 3. We're going to write down a general definition or principle. Now that often means a law, that often means a triple equal sign. I've talked about that with some of you, so maybe some of you I haven't, but we're talking about things that are true, that we're talking about now things that whenever they're true at all, let me say it again. We're talking about things now that are always true. They might not be always relevant, but they're always true. We're not yet even jumping to the particular numbers of the problem. We're not jumping to the specific circumstances of the problem. We're first going to write down something that is generally true in this step, right? So for example, like the question was asking about force, right? And so often what we're writing in this step is some kind of an equation. Often that equation will have a triple equal sign in it, not a double. But whatever kind of equation we're writing here is going to be general. It's not going to have numbers in it yet, almost never. And it's going to be something that is true even if you're not in this particular problem, right? So we're looking for force here. Question 1. Am I getting confused? Sorry, hold on 1 second. Yeah. Okay. Question 1 is asking us for force. So what I want to write down here is something about force, particularly in a spring, that is generally true of springs, regardless of these numbers, right? So in this case, okay, now, like we're starting to progress through the problem here. And again, I know, and I apologize, I know if any of you, if you did this homework at all, if you got any kind of answer to question 1, you probably got it right. And you probably didn't spend as much time writing things down as I'm spending talking right now. I get that. Like if you did it at all, you might have looked up something on the web. You might have gotten this equation that I'm writing it down. You might have written it and got an answer in 2 seconds and moved on. And it looks like here I'm totally dragging this all out. But again, I'm dragging this all out so that we have a thing that we know to do when things aren't as easy as right now. Okay, number one. Number two, I also want to acknowledge that this equation that I'm writing here, like, okay, now it is true. And it is the right thing to write for right now. This is called Hooke's law for a spring. It says F equals negative KX. I'm going to talk about it now, but I also understand that some of you never saw this before. If you had me or say you never saw this before until maybe you found it on the web this weekend. I get that. So let's try to put it in focus of what it is, but it is the right thing to write right now. And one way you might have found it on the web is you might have been doing mentally what we're doing right here, which is like, well, I know that I've got a problem with springs. I've got a spring, it's got a K. He asked for a force. So there's got to be something out there in the world that is true about springs and maybe even involves Ks. And so you did the right thing. Now we're just trying to put this in focus. Like, yes, what you were looking for was some kind of general principle or definition that applied to springs. And this is what you found. There's this thing called Hooke's law for a spring. That's what you would write down right now. Now notice still, we're 3 steps into the 5-step method. We're 3 steps in. All of the stuff that I'm dragging out that you would have done, all of this is points that you get. And we haven't gotten an answer yet. We haven't solved the problem yet. And all you have to know to this point to get all these points is you have to know what the question is. And then you have to find something that is generally true that relates to the question, right? Which many of you did on the web or in a textbook. We haven't solved or applied anything. We're just finding a general truth that applies to this problem. And here's the thing. At this point right now, Hooke's law, F equals negative KX, whether or not you fully think you understand it, it is a law. It is true. It's true. And it's vaguely topical, like it has something to do with what we're talking about here. So it is points because it's true. It can't be wrong. It's not wrong. All that might happen is we might apply it wrong. But because it's true, it's points that you get. Please notice what I'm trying to emphasize is the thing is I can't emphasize enough that just please note, it sounds so obvious. Everything sounds easy when things are easy. And everything sounds hard when things are hard. The real trick, and whenever I'm talking like this, I know it seems like what I'm doing as a physicist is taking easy things and making them hard. I know it feels like that's what I'm doing right now to anybody who's still paying attention. It seems like I'm taking something easy and making it hard. I cannot assure you enough or emphasize enough that actually what I'm attempting to do, even though it feels that way, is I'm attempting to show you how what physics really is in the long run. Physics is an attempt to take things that are hard and make them easy. But the way we do that, the way we take hard things and make them easy, is we spend a long time investigating what our own brains are doing when things are easy. Physics is really into dwelling on the easy, obvious, simple stuff, because while watching our brains do what they do on the easy stuff, we take those movies of what our brain's doing, we slow them down, and then we have a process to apply to when things are hard. And rather than without physics, what people tend to do is the harder things get, the more they panic and the more they drop all the tricks that they had going for them when things were easy. A classic example of that is on exams. On exams in science, when people get nervous, when I get nervous, when I get anxious, what I tend to do in exams, I look at a question and I don't know how to answer it. And I don't know where it's going. And I might not even know what it means. So I freak out and I start writing down things that I think have something to do with the question. And then I start contorting them. And I mean, I don't know I'm doing this, but this is what I do. When I'm panicking, I write down a bunch of things that I think maybe the professor wants, or maybe the question's sort of related to. I write them down, and then I start tweaking them algebraically or manipulating them algebraically until they start looking like something maybe right or true. That's what I do when I panic or when I'm nervous. But actually, what we want to do is be always in the habit of writing down things that are true and then manipulating them to make them relevant to the problem. So that's what we're doing right here. We're writing down something that's true, and then we're going to apply it to the problem rather than try. Okay, like that's that. And it's really important. The harder things are, or the less calm you feel in some moment, remember this: you first just write down things that are true, and you get points for them because they're true, they're not false. Then you start applying them particularly to the particularities of the problem. Now, we're going to do that on the next step. In fact, let me just think for a minute. Yeah, just so I don't lose anybody, I'm going to go to the next step and apply and get to the fifth step and get an answer. But then I also want to say this f equals negative kx. When we're done with this one question, we may not get that much farther than that. I'm going to get an answer to this one question just so you can know that you did it right or whatever. But then I'm going to back up and try to explain what this equation like actually means. Well, I'll give a brief overview right now. What this equation is saying okay. Oh, chat. Hold on a second. Great. Well, pardon me for a second. Chat. Yeah. Okay. Wait, great question in the private chat. I won't read the name because it's private chat. But so there's a great question in the private chat that says, if we negate kx, if there's which we do, there's a negative sign before the kx, does that mean we will get negative force? So the question in the private chat says, are we going to get negative force? The answer is yes. And that's a very great question. And I want to talk about that. The answer is yes. And let me be clear though, negative in physics means a particular direction. And direction is defined by the user, so to speak. So in this problem that we're looking at, that's a great question. And it's great that there is a question, and keep them coming, please. Again, I'd rather this be a dialogue than a monologue. So anyway, so now I'm going to like dwell on the question for 45,000 million years and make the person regret that she or he ever asked it, but not on purpose. In this problem, positive means to the right of 0. Negative means to the left of 0. Positive means, in other words, the direction toward which the mass was initially displaced, initially held away from equilibrium. What this law means, This law is like the definition of what it means for something to be elastic. This is in a sense the definition of elasticity. What this law is saying is that when material is elastic, it tries to restore its orientation back to equilibrium. Elastic material wants to be here. It doesn't want to be here or whatever. A spring wants to be, is at rest at a certain specific length, what we call its equilibrium length. If we start displacing the edge of the spring to the right, as we are here, if we start displacing the edge of the spring, we put a mass on the edge of the spring and we start displacing it to the right, what elasticity means, what it means for this spring to be a spring is that the spring begins to pull to the left, right? The negative sign is saying, really means in the opposite direction from displacement. X refers here to displacement. So we pulled out the mass, the edge of and I'm talking to everybody now, like I'm answering this question, but he's like totally helps. This is what I was going to say to everybody, like don't tune out just because you weren't the one asking this question. We pull the mass away from zero. We pull the mass and we hold the mass to the right of zero. The spring exerts a force to the left. That negative sign means opposite direction from displacement. And the word we give that in English is restoring. This is a restoring force because by the way, if we had pushed the mass to the left, which we could have, it's called compressing a spring. If we had set up the mass so that it was like 15 centimeters to the left of the equilibrium, then the spring would pull to the right. It wants to restore back to equilibrium. So the force exerted by elasticity by the spring will always necessarily be in the opposite direction from displacement. And in this case, that means negative, yes. And so in this case, the answer that we're going to get when we multiply the numbers, and of course, I know you all can multiply the numbers. I know I'm just like dragging this out and boring you to tears. But when we multiply the two numbers, we're going to get an answer that, yes, is going to be negative. Our answer to this is going to be negative 30 newtons. And what the negative just means is that the spring is pulling with a force of 30 newtons to the left. Like that's what that means. And that is correct. 30 newtons will be the answer. I mean, I haven't written it down yet, but that will be the answer. So this law is the law of how the spring force works. Notice we've had other forces in physics. We've had the gravitational force. We've had the frictional force. Some of us, yeah, we've had the frictional force. We've had the tension force, the normal force. There's all kinds of forces in physics. All forces in physics all ultimately are subjected to Newton's second law of motion. All forces contribute to. Okay, great. Oh, thank you. Thank you. That's awesome. That's total class participation points. Thank you. Okay. So now moving on. So, okay, the question's answered. That's good. So now I'm just moving on to the whole class to everybody. But thank you. Like everything I just explained was kind of explaining the negative. Now I want to kind of explain what the K is all about. Okay. You have the force of gravity is like the force mg, or the force of weight we said last semester, or the force of friction is mu times the normal, or things like that. So we have different equations for different descriptions of different forces. And the thing that's in common about all forces is that all forces contribute to the left side of F net equals ma, right? Like the whole point of forces is that you make a free body diagram, you account for all the forces acting on some object, and the sum of all of the forces acting along a particular axis, a particular dimension of space, the vector sum of all of those forces, taking into account minus signs, ultimately yields the acceleration of that object along that axis. Like F net divided by m will produce the A of a particular object. So all forces, what they ultimately do is contribute to the net force on an object, which produces the acceleration of an object. So different forces come from different things. We're now talking about the force that can be exerted by a spring. And what we're saying now for the first day, this is not meant to be a very complicated equation, but it is a new equation for many of us, and it is an equation. It's saying something. It's saying that the way the spring force is, it restores objects, or it restores orientations to an equilibrium orientation. And it does so in a variable fashion. Please note, like the illegible red thing that I wrote to the side, what I wrote here is on the side in red, elastic forces are not constant. They are, but however, they, semicolon, whatever, they are as simple as variable forces can be. Now, what the heck am I saying with that? I'm saying, like, back in the day from first semester, we could say that the weight of an object is mg, right? It's mass times 9.8 meters per second squared. Now, whether you like that or not, what we were saying back then is like the force of gravity on this object right here, its weight is an amount of newtons that's pulling this object down toward the center of the earth. If this is a 2 kilogram, if the mass of this object is 2 kilograms, then right now Earth is pulling down on this object with a force of 2 kilograms times 9.8 meters per second squared, i.e. approximately 19.6 newtons of force it's pulling on this, right? I mean, just an example, just to remind you of like how forces are like, but now here, now note this, even if I hold this object up here above my head, I mean, within reason, if I don't get too crazy and too far away from the ground, if I hold this object up here above my head, its weight is still mg. Its mass, 2 kilograms, times 9.8 meters per second squared, 19.6 newtons. Whether I hold it here, or I hold it here, or I hold it like a lot closer to the earth, the weight of this object, the force of gravity applied to this object is approximately 19.6 newtons or whatever number, regardless of how far away it is from Earth. It's approximately a constant force, gravity. Now, I mean, once you get far enough away, that starts changing, but I'm saying within reason, that's the case, and that's how we treated it last semester. Similarly, friction, if there's something sliding on the table, whatever friction the table is exerting on that object is whatever friction that table is exerting on that object, regardless of whether the object is here or here or here. Now, for the first time in our lives, and again, you may have just found this on the web. This might be mathematically very easy for some of you to deal with, or it might be old news, but I just want to drum in that this little equation here, F equals negative kx, Hooke's law for a spring, what it's saying is that what it's really defining what elasticity is, and it's saying elasticity is a variable force. The nature of elasticity is that it is a force that gets stronger and stronger as you get farther and farther away from a certain place or a certain orientation. When you go to the gym to lift weights, or to, I'm like, I don't know anything about that, but I've seen movies, but, or like if you do, like if you play with, if you work at equipment in the gym, a lot of that equipment is based on all kinds of spring and spring loaded mechanisms and things like that. And the whole idea of springs is that if one end of a spring is fixed to the wall here, for me to hold the spring out here is hard. I need to exert my muscles to hold the other end of the spring out here, or in this problem, in this homework problem, to hold the mass at 15 centimeters. I've got to exert some strength. I've got to exert some force to match the force of the spring and hold it there. But if I tried to hold it farther away, I would have to exert more force. It's unlike gravity, where it doesn't matter whether you want to hold the can here or here or here. It's the same weight. With a spring, if you want to hold it here, it's a certain amount. Here is harder. Here's even harder. It's a variable force. That's what the first thing we're saying. F depends on X. It's not constant, depends on X, all the way to the limiting case, the extreme, where if X is 0, if the object is at equilibrium, then there's no restoring force at all. Like K times 0 is 0. The force is 0. So as you get farther from the equilibrium, the spring exerts a greater and greater magnitude restoring force, greater and greater magnitude, but always in the opposite direction from displacement. Hence, we say negative kx. Now, I want to dwell on this one more minute. Again, whether this is new or old to you, I'm now like from here on in, hopefully this is clear. What we're really saying is how elasticity works. Okay, just to make this as clear as I can, let me also say this page that I'm on right now and the last page, you can make a note, like, so this page right here that's on the screen right now, this page right here, and this page with the graph is me teaching, is me explaining, is me expanding. I'm not saying all of this you would have to include in the homework, although you certainly could, especially if you were learning it for the first time or on an exam, you certainly could and should if you really want to both show me that you really know, and also if you want to guard yourself and protect yourself because you might not know something later on in the exam, you certainly could include all this. I'm not saying that you have to include all this, but what I'm doing here is expanding on the general definition of principle known as Hooke's law. So these 2 pages you don't need to include in your homework, but I'm trying to say to you what this general principle means, especially again, because I know some of you just found it on the web like this weekend. So what I'm saying is, oh, and I should say, sorry. Like if we were to grab, or a technical, okay, sorry, let me actually, hold on. If I really want to be right about this. I don't know which, in some ways, I don't know which is more confusing. Technically, this line should be going down under the x-axis because technically it has a negative sign on it, just like someone in the direct chat just asked about. If the negative, so technically the force goes in the opposite direction of the displacement. If you don't like that, if that throws you off, you can just put absolute values around the F on the y-axis and put the line back in the first quadrant where I had it. But here's my real point is that this line, wherever you put it in the first quadrant or the fourth, it's a straight line. What we're saying is that the restoring force, the elastic force, is variable. It's not constant, but it's as simple as a variable force can get. It varies, but it varies directly proportionally to the displacement. It's not like F equals kx squared or x cubed or cosine of x or anything like that. It's just kx, which means that the ratio of force to displacement, the rise over the run, like the increase in force that the increase in number of newtons of force that you get for every increase in meters of displacement is a constant. Like if this is like this is like y equals mx plus b, where b is 0 and where y is like f, x is x, and m is k, if you see what I'm saying. So k, that k number that again, some of you never saw before this week, that k number is the slope of the force displacement graph for any elastic material, for any good, nicely behaved spring. K is that constant of proportionality. It is a constant. It is measured in newtons per meter because it's literally what K is. If we said in this example, this problem, K is 200 newtons per meter, we mean for every extra meter of displacement that you subject the spring to, the spring will exert an extra 200 or an additional 200 newtons of restoring force. So K is a mathematical constant, but it's also the physical identifier of the spring. K is what is known as a parameter. A parameter is a kind of constant. There's different constants in the world. A parameter is a constant, but there's different types of constants in the world. There's like Planck's constant, which is a constant in the universe, right? Or, there's constants that are always constant, but then there are constants that are constant for a given material. Like I'm not saying that all springs have the same K. They don't. But a given spring can be identified by its K. K is its constant material property. It's a description of that spring. And specifically, K ultimately describes how stiff or strong a spring is. The higher the K, the greater force it exerts for each meter of displacement that you try to subject it to. So 400 Newton per meter K is a stronger, stiffer, tighter spring than a 25 Newton per meter K spring. That would be a very loose spring. Okay, so ultimately springs now could be defined by their K. That's how strong they are. And every well-behaved spring will obey this F equals negative KX in this fashion. All of that is me talking. That's me just trying to get you to understand what F equals negative KX is. Again, you wouldn't have to write that all down in homework, but I'll tell you this. Once you've looked up, once you've written down what the general definition or principle is for a question, especially if it's an exam, wherever you got that general definition or principle, whether you got it from me in class notes or from the web or something, you definitely want to make sure that you go through something like what I just went through to make sure that you actually can physically picture what that definition or principle is. Like, and you should give me some kind of communication on that. It doesn't have to be all this, but we don't just want to plug and chug is the point. We want to understand and picture what we're doing and then apply it. So now I feel, okay, so from here on in, even if you never learned F equals negative KX before, or even if you're seeing it for literally the first time now because you didn't do the homework yet, or even if you just grabbed it from the web or from check or so, sorry. Oh, okay. I'm going to get the chat in one second. But I'm saying now, for whatever it's worth, I feel that I've taught it to you. I mean, to be official, like now we've learned, as far as I'm concerned, we've now learned everything there is to know or use about Hooke's law for springs. From now on, all springs obey this F equals negative KX. And now let me just, I know there's a question in the chat. Sorry, let me, but so now we're responsible for it from here on in. Sorry. Sorry. Yeah, good question. So in the denominator of the fraction up here in my notes, it's trying to say rise over run. Here, let me, so I'm trying to say, I mean, good question. Very good question. I'm trying to say rise over run. Like if this were a regular, and maybe in the direct chat, if you could tell me if that answered the question or if I'm about to, but like if this were a regular math class and you just had some graph, y-axis, x-axis, and you just had some regular graph. Oh God. Okay, cool. Thank you. Okay, thanks. But so to everybody, here's the connection I'm trying to make. Like in math, you learn, you about slope. Slope is y2 minus y1 over x2 minus x1, or put another way, delta y over delta x. What is slope? So it's like how much we change in the y value versus, or divided by, or per how much we change in the x value. That totally applies here, only on the y-axis, we're measuring force measured in newtons, and on the x-axis, we are measuring x displacement measured in meters. So I'm saying like the slope of this graph, of the force to displacement graph, the slope is what we ultimately mean by K. The slope here is the constant rate of change of force per displacement. And so that's what K is mathematically. And then physically, that's just how freaking strong a spring is. How much force does it exert per every extra or additional meter of displacement? And again, notice, so this is just like y equals mx plus b. It's a linear relationship, and it's nice because b is 0, like the y-intercept is 0, meaning when there's no displacement at all, when the mass is just sitting at equilibrium, then the spring doesn't exert any force at all. It's happy. Okay, so that's okay. That's in the chat. Okay, I'm gonna go on. And I know again, okay, cool. Again, I know this is, for some of you, I know this is torturous that I'm just dragging this out like this. I apologize. I don't know what, but also for some of you, it's not. I mean, and I'm trying to talk to both of you, but also please everybody note, I hope you saw last time, these are now, I don't remember if Professor Jay Walters did this or not, but all of this is going on YouTube. Well, the notes from this is in a PDF that will go straight to your Google Classroom when we're done today. I do hope you're taking your own notes, especially because mine are illegible and crazy. I hope you're taking your own notes, but everything I said, this screen will be in a PDF that will go into your Google Classroom when we're done, like literally done today. And then this whole discussion will be uploaded to YouTube. Like that takes a couple hours and sometimes days, and it'll be on YouTube and linked to your Google Classroom as class number 2 or whatever when we're done. So you can go back. And so why am I saying, and hopefully you already saw, I think the first class was already put there. I mean, it wasn't a particularly informative class, but I think it's there. The thing about this is, please also notice, especially if you don't know me, I'm trying to go over the homework right now, but part of the reason I'm going really slowly too is I'm also trying to use this homework as an example of the larger 5-step method. So this would be the lecture. If you ever want to go back to the 5-step method, because I want to use it all the time, like this would be the lecture to replay, and this would be the PDF to reinvestigate. Like this is the 5-step method for everything going forward. And what we just did was step 3. We did all the stuff. We haven't solved anything yet, but we already did 3 out of the 5 steps. Now we get, and I know there's 9 minutes left, which is actually perfect. So we're going to get 1 question done today, and then there's nothing new assigned besides the game turn tonight. Just stay on this homework and keep working on it, and we'll continue this on Wednesday. But so now we get to step 4. Step 4 is what I call PAW. Okay. Okay, so here we're going to finally apply. Here we're going to take our general thing and apply it to the specific circumstances and values of this problem. So I'll cut to it again. So here's where you start subbing in and plugging in and all that. So here we said, so now we're back to the actual problem right here. We said f equals negative kx, right? So here we can say, okay, so here we're plugging in the 200 for the K, the 0.15 for the X. And I know, again, many of you could do this part without any of the explanation or any of the thing I just said for all the 3 steps. But what I am saying is, this is the part that a lot of people consider the work. Like when they think, oh, I got to show my work, they think, show this. I'm saying don't even start this until you've done the other 3 steps. The other first 3 steps seem really stupid when you already know the answer, but they are the thing to do when you don't already know the answer. Okay, I can't say that enough. Like before, a lot of times people, and I know there's only 6 minutes left, but I'm going to say this because I love to say this, because I love to hate to not say it. I'm going to say a lot of times as physics gets harder and harder, and it does get hard in physics 204, and questions start getting to the point where people say, well, I know what he's doing in class, or I know how to do physics, or I know how to plug in equations, but I never know how to start his questions. I don't even know what they mean. I don't know how to start. What I'm saying is that's because people think that starting to do a question is to dive right into step number 4. The way to start a question is to do steps 1 through 3 first. Don't even try to do 4 until you've done 1 through 3. And once you've done 1, 2, and 3, they will set you up and lead you to showing the work and plugging and chugging and all that, blah, 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 blah. So now, yeah, we're going to plug in these values, 200 and 0.15. That's PAW. And now we're just about done with the whole thing. So we plugged in the particular values. Now we're in a double equal sign. Technically, we've been in a double equal sign this whole time because of this particular law, but usually laws are triple equal sign. Okay, so we've done that. So now we go to step 5, and I know there's 5 minutes left. We're just about there. Step 5. And this is FAC, final answer circled. So now we finally can say, okay, our answer to this and the end of the whole thing is indeed 30 newtons, and include all your units and all that kind of stuff, and negative signs, positive signs, but here's the final answer to this question. And this is the final stage of this process. And again, there's like 4 minutes left, but so this was question 1. The answer to question 1 was negative 30 newtons. Notice the final answer is a complete thought. Like, notice this, the step right at the beginning of this whole thing, the question was I could even say actually at t equals 0. Maybe I should be more clear. At t equals 0, I plugged in 0.15 for x. So my final answer is at t equals 0, F equals negative 30 newtons. The original question is, when t equals 0, what is F equal to? The final answer is at t equals 0, F equals negative 30 newtons. I've brought it full. Oh, sorry. Can I also write to the left? Can you also write? Oh, right to the left. Oh, that's a great question. Sorry. In the private chat, someone wrote, can I write to the left instead of the negative sign? Yes. As long as you absolutely make the direction clear one way or the other, yes. For the final step, yes, you can. Just absolutely make the direction clear one way or the other. And the one other thing, though, is, so yeah, you could write to the left, but it's not a horrible idea to keep the negative sign, because remember, this is question 1, and the rest of the questions are probably going to be, or some of them are going to be based on question 1. So it's not a horrible idea, really, to keep things like negative signs involved in your answer, because you might want to be tracking them later. But yes, this negative means to the left. You could write to the left. That would be fine. Yes. So note to everybody, this is the process. You start with the facts and the diagram of the question, then you say what the question is, then you say a general definition or principle that relates to that question, then you apply that general definition or principle to the question, then you get an answer to the question and you circle it, and I should be able to look at this whole thing and see, aha, yes, their final answer did relate back up to their original question. And here's the deal, again, with 3 minutes left. If you do all of these steps, you can get to a final answer that's totally wrong and still get all the credit because you are working your way through the problem. You might make on the homework you can. Or you could have just written down, for the future, once we all get used to each other and stuff, it's true. I know many of you could have just written down negative 30 newtons in your head right away just for question 1, and you could have just left it. And I believe you that you weren't cheating, but I could still take off points and would, because the easier it is, the more good reason there is for you to use the easiness of the question as a practice for doing this method, so that you know what to do when you finally, eventually, someday don't know what to do. Okay, so for everybody, you can get all the points without a right answer, but you can also lose points if you're missing steps. It's about the process, certainly at least on homework. And of course, you can all work together and should work together. And of course, you can use the web and all of that. The idea behind this method too is that everything you're writing, you're showing that you understand. So I don't care where you got the knowledge, as long as by the time you write it down, it is knowledge and understanding in your head. It's not just raw, weird, black magic information. Okay, now obviously we've only done one question. We'll continue with this on Wednesday and we'll go faster. I'm not going to rewrite this whole method, each time. If ever on the homework, if I just write somewhere like -2 WIQ, then you now know what it means. Like, this is the grading rubric. If I write WIQ, I mean, what's the question? And that's why I took off 2 points, blah, blah, blah. So if you still can totally submit the homework. If you haven't yet, you can resubmit. If you feel like a better way of doing it now, do this. We will just continue on Wednesday from question 2. The only other new thing that's due is please put in a game turn assignment for tonight. I will catch up and get back to you. Your game turns. I'm done. I'm going to hang out for a couple minutes if there's any questions at all or any logistics or anything. But thank you. Yes. Okay. Thank you. Take care, guys. Thank you. Have a great day. Good to see you. And I'll post all this.
Professor, I have a question.
Yes. And let me just turn off the recording.